Welcome back, my dear students. In the next class, in the last class, you just remember we have to discussing this theorem, and we already discussed this first three properties of this theorem, and then we have to discussing the this last two properties today lectures and the sum. So let us begin with this. We begin with the part of a D. We have to this the we have a given this clearly h of g1 is equal to h of g2, and then g1 is the element of a h g1, and if g is the element of a clearly g1 is the element of h of g1. G1 can be written as a E of G1, and E of G1 is the element of H G1. So clearly this G1 is the element of a, and then you can say G1 is the element of H of G1, and H of G1 is the same as H of G2. This implies that H of G1 is the element of H of G2. If G1 is the element of H of G2, G2 can be written as sometimes of H of 2, for some H is the element of H. So if some H is the element of H, and G1, G2 are the element of a G1, and G2 are the element of a group. So this means can be we can write into the form of a this. So we have a write in the G1 and G2 inverse is the same as a H G2 and G2 inverse, and then we can write H of G2 inverse is H of, we have an identity, and this is equal to H, and this is the element of H. So we finally show that this G1 and G2 inverse is the element of H, and hence G1 G2 is the element of H. Now we have to try to conversely, if we have a G1 G2 inverse is the element of H, so we can say simply is equal to in this form. We have a if we have a G1 G2 inverse is the element of H, then we can say that simply H of G1 can be written as a H of G1 G2 inverse and G2 by the, because it's this we write in the form of a identity H of G1, and then is H of G1. I just write like this way, we can write in this form. We have to H of G1, this can be written as a H of G1 into identity, this can be written as a H of G1, and we have to write a G2 inverse, and then we write is a G2 by the associativity condition hold here, and this can be written as in the form of a, and because you just said that this G1 G2 inverse is the element of a H, this is the element of H, and H is the element of H. So this means we can say that simply is equal to this H G1 and G2 inverse hold the element of H. If hold the element of H means we can simply say that this complete is the element of a H of G2. So we show that H of G1 is the element of a H of G1. So we can say that H of G1 containing to the H of G2. Now similarly, because we just say that you know that the property we have a clearly you just check now we have to clearly G2 G1 inverse can be written as a G1 G2 inverse ka whole inverse. And now you know that this G1 G2 clearly G1 G2 is the element of H. If these two are the element of H, then the inverse of this also the element of H. So this means this clearly this is the element of H. If this is the element of H, means we can say that this implies that G2 G1 inverse is also the element of H, and we have a G2 G1 inverse is the element of H. So we can simplify this. We can start from the again the similar fashion. We start from the H of G2. H of G2 can be written as H of G2 can be written as H of G2 into identity, and then we write G1 inverse and G1, and then we have to take associativity H of G2 G1 inverse. Now we have to show that G2 G1 inverse is the element of H. So 2, that means this is the whole thing is the element of H. If this whole thing is belongs to the clearly is H, and G1 is there, so this means whole thing is belongs to the H of G1, and then we have to show that H of G2 containing into the H of G1. So we have to proving these two, then H of G1 containing H of G2 and H of G2 containing H of G1. Then we can, by the set theory standard property, A containing B and B containing A always implies that A is equal to B. So we simply we prove this D part also. Now we have to prove the last part is equal to G1H is equal to G1H is equal to H of G1, and then H can be written as a G1 G2. So we have this G1H is equal to this if and only if we have to write in H if and only if this H can be written as a G1H G1 inverse. Now because you have a G1 and G2 are the element of a G, and these two are the element of a G, means is a group, and then G1 inverse and G2 inverse is also the element of a G. So we can write a G1H multiplied by inverse of this in the both side. So we can say that G1H G1 inverse, then H of G1H, now use the associativity here, then we can say that G1 inverse, then we can say that this is simply is equal to H, and then if we have a H go the reversely, if we have a H is equal to, we have a G1 H of G1 inverse, then H of G1 is equal to G1 H of G1 inverse, then we have to multiply it by this side H G1, and this is nothing but the G1 H, and then we have a G1 inverse G1, and then we can write as a G1 H, and this is equal to identity, so this is equal to G1 H. So both the way we have to show that if we have a H of H is equal to G1 G1 inverse, then we can show that simply is equal to H of G1 is the same as the G1 of H. If H of G1 is equal to H of G1 H is equal to H of G1, then H can be written as a G1 H G1 inverse. So this complete the proof of the this theorem. This theorem is we have to using these are the very basic properties of this cosets. We have to using this results is many times without the mentioning into this. Nextly, we have to prove that the very important results, we can say that let if G is a group, let G be a group and H is a subgroup of G, then any two right cosets of H in G are either identical or have a no common elements. Means we can say that either identical or have a disjoint. Okay. So no common element means there is a their intersection is a disjoint. So these two cosets are, and then similar result can be hold for the case of a any two left cosets of H in G are either identical or have no common element, or they are disjoint. So we have to prove the two things. If any two right cosets are the same, then we have nothing to prove that. So we have a, if we have a any two right coset and these two right cosets are the same, then we have nothing to do, we have to prove that. Now if we have to other way, so let H of G1 and H of G2 be any two right cosets of H. If the intersection of this is equal to empty, then the result is proved. Then we have to nothing to do. So we have to prove that if intersection of these two is equal to then they are disjoint, and that disjoint means there is no common element, means these are not the same, then we can say that this is the proof clearly. If they not the same, then intersection of these two is empty, so this is result is a proof. Now with the result is this, we have to just say that if in this intersection is not empty, if intersection is not empty, we have to show that then H of G1 is the same as H of G2. So we have to from, because if intersection is not empty, then they are identical, because the theorem is saying that if we have a G is a group and H is a subgroup of this G, then any two right cosets are identical or have no common element, or they are disjoint. So if they are disjoint, then result is trivial. Now we have to assuming that they are not disjoint. If they are not disjoint, then intersection of this is equal to not empty. Let X be any element of in the intersection, then by the property x belongs to the H of G1, means x is the element of a G1 and x is also the element of a G2. So if x is the element of a G1, Hg1 and x is the element of Hg2, if x is the element of Hg1, x can be written as a H1G1 and x also can be written as a H2G2 for some H1 and H2 are the element. So you just see this, you can just say that we can say that we have a x can be written as a H1G1 and x also can be written as a H2G2. So if belong to the intersection. Now we have to show that this is x is nothing but is equal to this x is equal to you have a. So let y be an arbitrary element of H of G1, and then if y is an arbitrary element of H of G1, then y can be written in the form of a Hg1 for some H is the element of H. So y can be written as H of some G1, and now you just see that we have to write in the form of this x is, we have to write in the form of this x is equal to H1G1. So we have x is equal to H1G1 and x is equal to H2 and G2. So now from this we can say that H1 and H2 are the element of H. So if H1 is the element of H, then H1 inverse is also the element of H. So this means we can write this from this is H1 inverse, X can be written as a H1 inverse and then H1 and G1, and then it can be written as a by the associativity property H of G1 and then is equal to identity is equal to G1. So we can say that G1 can be written as a H1 inverse X, and similarly for this we can say that G2 can be written as a H2 inverse X. Okay, so we have to. So H of G1 and then G1 can be written as a H1 X inverse. Now this is equal to H1 H1 inverse is equal to identity, and then X can be written either form which is H2 and G2. So if H2 G2 X can be written as H2 G2, then we have a this can be written as a H1 inverse H1 inverse H2, and now this is the element. Now H is the element of H, H1 is the element of a H. This implies that H1 inverse also the element of H, H2 is the element of H, and H is a clearly is a subgroup of a G. Then we can say that H, H1 inverse and H2, these all are the element of H. And if this whole thing is the element of H, we can simply say that this quantity is the belong to the H, and then this is G2. This means whole thing is belong to the H of G2. So this means y, we can take a y an arbitrary element of H of G1, and then we show that this y is the element of H of G2. Then we can say that we have to simply say that H of G1 is containing into the H of G2. So reversely, we have to just take y is the element of a sum, y is the element of a sum H of G2, and then y can be written as a sum H prime of G2, and then we have to this can be written as a H prime, and G2 can be written as a, we have a some G2 inverse, and then we have a X, and then this can be written as H prime H2 inverse, and X can be written as a, we have to write as H1 G1, so H1 G1, and then this can be written in the form of similarly this here. Okay, so now we have to just conversely we have to take y is the any element of H of G2, then if y is the element of a G2, then this implies that y can be written as a some H prime G2, some H prime is the element of H, and then G2 you know that the X is equal to, you have a H2 G2, then you have a G2 can be written as a H2 inverse X. So this can be written in the form of a, we have to write this this y is can be written in the form of a H prime, and then G2 can be written in the form of a H2. So this can be written as a H2 inverse, and then X can be written as a H prime H2 inverse of X, and X you know that X is equal to, you have a H1 and G1, and this can be written as a H prime, and then H2, and then you have a H1 and G1. This can be written as a H prime, and we have a H2 inverse, and then H1 of a G1. And now you see this H1 prime is the element of H, then you have a H2 inverse is the element of H, then you have a H1 is the element of H, then by this we can say that H prime, H2 inverse, and H1, this is all the element of H. So this complete belongs to the H, and this is the element of A, belongs to the H of a G1. And then Y is the element of a H of G1, but Y is the element of a H of G2. So we can say that H of G2 is containing H of G1, and by these two we can simply say that these two are the we have to just say that H1 G1 is equal to H2 G2. So this means H1 and H2 are not a disjoint. So clearly we can say that when H1 so if H1 and H2 are disjoint, then the proof is trivial, because the theorem says that if the both the left and right coset are not the same, then they have no common element, and then means if we have to assuming that suppose they are not a their intersection is not empty, then we have to try to solve that. If his intersection is non-empty, then both the right cosets are the same. This means H of G1 is the same as a H of G2. So now we have to complete the proof of a this theorem. Now we have to come to the next theorem. We say that let G be a group and H is a subgroup of a G. Then the union G is the union of all. You know that we have to prove various examples take in the beginning, and then we have to take, if you remember, I take a group is a set of integer under addition, and we have to take H is related to 2Z under addition. Then there are the only two different subgroup. We have a like this two, because there is a left and right coset are the same, because these are the group is abelian. So we have a H and H plus 1. So we have a only these two are the this H and H plus 1. So we have a, if you take this union of these two H and H plus 1, and this decomposes this, and clearly we can say that H and H plus 1, and this is clearly is equal to empty. So intersection is empty, that means these are the two different right cosets. Then the previous theorem is showing that their either their intersection is equal to empty, or they are they have no common element, or they are identical, or they have no common element. So by this example we can clearly say that. And also if we take a union of these two, and also you have a in this symmetric group we have a three different cosets are there, and then that union of this again giving you the S3. So in this case also we can simply say that if we take a union, so in general we can say that if we have a G can be written in the form of a union of all the right cosets of this C. So G can be partitioned into the all the right cosets of a G. If we have a, if similarly we can say that G can be partitioned of the all the left cosets of a H in G. So let's prove that by sin, because you can say that G is a so H of G1 is clearly subset of a G, and for any G belongs to G, if we take a union of this, if H of G1 is the element of a G, then for all G1 belongs to the G, a union of all this right H of G1 is also contained. If this element is containing, then H of G2 containing. For all G1, this H of G1 is the element of this union of all the G1 is clearly contained into the G. So now for also for any G can be written as a EG, and EG identity into G, and identity of G is the G, and this is the element of H of G. So we can say that simply is equal to G can be written as a E of EG and is the element of H of G. So we can say that G is the element of union of H of A. So G can be the element of HG, then the G is in the element of HG, then G must be the member of the union of all G1 belongs to HG. So this is the H of G, sorry, not A. Okay, is the H of G. So we can say that this G is the element of this, so G is the element of a union of this all of HG. Thus G can be, if G is the element of this and G is the element of a G, that means G can be a subset of a union of all of H of G1. So if all of H of G1, so we can say that this is the G1, okay, this is not that. So this proves that by this and this is suppose we have a 1, this is suppose we have a 2. So from 1 and 2 we can say that G can be partitioned into the union of all the subgroups of all the right cosets of this. So these G's can be written as a, then G is the union of the all the right cosets of H in G. Similarly, we can say that G is the union of the left cosets of H in G. We can prove both the result in the similar fashions by using this the definition of this thing. Okay, now we have to just remark that it's important to recognize that despite potentially differences between the right and the left cosets of H, they invariably contain the same number of elements and exist in equal quantities. So this remains true universal when the set then the cosets are infinite in a size. Also, if we have two sets A and B are said to be equal cardinality or have the same number of elements, so we can say that if there exists a bijective correspondence between them, and in this case of a finite set, this implies they have an equal number of elements. The concept can also extend for a infinitely sets. So if we have any two sets A and B, and these two sets are equal cardinality, have the same number of elements, if they have there is a bijection between A to B, bijective correspondence between A and B, then we can say that the cardinality of A and the cardinality of a B is the same. So this can be not only for finite set, this can be extend for the infinite sets also. We come to this proposition, we can say that clearly H is be a subgroup of a group of a G, and G is the element of a G. Then any map we define from this defined by this is a bijective, and if it is bijective, then H and GH have the same number of a element. So we have to going to prove this result. First we have to show that the map is defined is a well defined. So this we have to just see that we have to phi is already is given, so we have to assuming that this is a well defined map, and then we have to show that this is injective. So we take a phi is injecting, assuming that phi of H1 is equal to, we have a phi of H1 is equal to phi of H2. So phi of H1 is equal to, you have a map is defined as a G of H. So we can cite that this kind of G of H1 is equal to G of H2. Now by the cancellation law hold, then we can say that H1 is equal to H2. So phi is clearly is a 1 to 1 correspondence. Now we have to show that next is this phi is injective. To show that phi is a surjective, next we show that phi is a surjective. So phi showing that phi is a surjective, observed by the definition of a GH, every element of a GH is of the form of a GS from some H is the element of H. Now since phi of h is equal to g of h, and then since it follows from the phi maps onto gh. So phi of map into g of h, we can say that some element of a gh is the form of a g of h. If we have a g of h, h is the element of h, and phi of h is equal to g of h. So we can say that g of h, this means phi maps up to g into h. So we can say simply that it follows that phi maps onto gh. So therefore phi is a bijection confirming that h and gh have the same number of elements. So if we have a h and gh have the same number of elements, if we have a find that the correspondence of this map is a bijective into this form. So we clearly prove this theorem, and then we can say this proposition, we can extend this result in the case of a we have a infinite sets are there. So this we have to prove. So we have to discuss properties of cosets, and then result we have to using only proof in the case is a right cosets, but you can easily prove in the case of a left cosets. So I have to stop today's lecture here, and I continue in the next class. Some more results we have to proving for the case of this cosets, and then we try to move to the very important theorems of this groups is called is a Lagrange's theorem, where we can say that proving into the coming lectures. So thank you for listening. I have to stop. Thank you very much.